All right, welcome back. In the previous video, we went ahead and proved that when x is even, the inductive step of the proof for the division algorithm does work correctly. So what we need to do now is consider the case of the inductive step where x is odd. If you haven't watched the first video, watch it because this won't make much sense. So we're going to go ahead and now assume case 2. We're going to assume x is odd. And there's going to be a few extra things that come up here, but it's not too bad. Note that the floor of x over 2 is going to equal x minus 1 over 2. It might be easier to see that as x over 2 minus 1/2 because we need to subtract away the extra half that we get when we divide by 2 in order to round down to an integer, but that's what it ends up being. And I didn't say this as clearly as I wanted to in the first step, so I'm going to say it slightly more clearly here. So we assume, as we set up here, that division runs correctly for all 0 is less than or equal to x prime is less than x. Since x, the floor of x over 2, is less than x, we correctly run, or we correctly find q prime r prime equals divide of, I'll write that as x minus 1 over 2, y. So that tells us that x minus 1 over 2 equals q prime y plus r prime, and r prime is less than or 0 is less than or equal to r prime is less than or equal to y minus 1. Now let's go ahead and in the previous proof what we did is we then multiplied both sides by 2. Technically we need to do a little bit more here. So we're going to solve the equation for x. When we do that, I need to multiply both sides by 2 and then add 1. That's going to get me that x equals 2q prime y plus r prime. So that's, 2r prime. That's multiplying both sides by 2. And then I need to move that minus 1 over. So that's going to turn into plus 1. And I'll add some parentheses here to show that really what we have is we're getting a quotient of 2q prime and a remainder of 2r prime plus 1. Okay, so we get that. And then if 2r prime plus 1 is less than or equal to y minus 1, we're done. Because we correctly return q prime and then 2r prime plus 1. And that satisfies all our stuff. X equals 2q prime y plus 2r prime plus 1. And in this case, we're assuming that 2r prime plus 1 is less than or equal to y minus 1. Which is obviously also greater than or equal to 0. Okay. Let's go ahead and just make sure that's what it returns. So we get q prime and r prime. We double them just like last time. Now that x is odd, we add 1 to this new r value. So now r is going to equal 2r prime plus 1, which is what we have here. We don't do this step, so we return what we need correctly. Okay, so that all works. If 2r prime plus 1 is greater than or equal to, or basically is greater than or equal to y, then we'll again note that x equals 2q prime y plus 2r prime 1, or 2r prime plus 1, we can do a similar trick to what we did last time. We'll add 1 here, and then we'll subtract y from here. Again, for very similar reasons, 2r prime plus 1 minus y has to be greater than or equal to 0. And here's where we need to be a little bit more careful. So we want to show that 2r prime plus 1 minus y is less than or equal to y minus 1. That's going to say 2r prime plus 1 minus y is less than or equal to, well, this r prime is less than or equal to y minus 1. So that's supposed to be a y, not an r prime. Plus 1 minus y. That's going to equal 2y minus 1 plus 1. Or actually, sorry, 2y, I'll write that out because I almost messed up. 2y minus 2 plus 1 minus y, which is going to be 2y minus 1 minus y, which then equals y minus 1. I'm going to give you a word of warning. I was very careful to use that r prime is less than or equal to y minus 1. If I use r prime is less than y, instead of r prime is less than or equal to y minus 1, this inequality won't work well. This inequality won't work. Because since we're talking about integers this whole time, instead of writing less than or equal to y minus 1, oops, didn't mean to erase there. Instead of writing less than or equal to y minus 1, I could have just been writing strictly less than y. The reason why I haven't is because we need it to be less than or equal to 1, or less than or equal to y minus 1 for this inequality to work out how we need it to. It's not that those mean different things, it's just that when I write less than or equal to y minus 1, I'm being a little bit more specific, and that specificity is going to give me the extra room that I need for this inequality to work out. Okay, so I don't want to belabor that point too much longer. We'll just finish by saying, since we have that x equals 2q prime plus 1, y plus 2r prime plus 1 minus y, and 0 is less than or equal to 2r prime plus 1 minus y, which is less than or equal to y prime minus 1. That's not a y prime, that is just a y. We correctly return we correctly return 2q prime plus 1, 2r prime plus 1 minus y, and for good measure, let's just make sure that's what the algorithm actually does. Okay, double it, we get q equals 2q prime, r equals 2r prime, and then we add 1, so we get 2q prime, 2r prime plus 1. Then, since 2r prime plus 1 is too big, we subtract y, so we get 2r prime plus 1 minus y, and then 2q prime plus 1, and that's exactly what we have here. Okay. So we can say, since both cases of our induction step worked, we've shown that the division algorithm is correct. And we're done. Woo. Before we end this video, let's also talk about the time complexity of the division algorithm. what's going to happen? Well, we make, before I say that claim, since we divide x by 2 in each call, we make basically log of x calls to divide. Since x is an n-bit integer, this is on calls. Because log of x, when x is an n-bit integer, log of x is going to be n. Each call involves doubling, which is essentially shifting. So I'm going to say shifting because we double things and we cut things in half. Adding 1 and subtracting y. Let's see if it does anything else. Okay, so doubling, great. There's our shift. There's our cutting in half, great. Here's adding 1. There's subtracting y. So we don't do anything more complicated than that. And each of these, each of which are also on operations. Because shifting, adding, subtracting, you at least need to read the number, which takes on operations, and then each of these things just involves like moving the number, basically shifting it in an array, or maybe changing one entry, and subtracting, adding, subtracting, you can also show that that is a linear time operation. So, since we make on calls and each takes on time, each taking on time, the complexity, or the time complexity, or I'll say the runtime, I'll write time complexity, is going to be on squared. So there we have it. We have an big O n squared algorithm for dividing two integers and getting the quotient and remainder. The last thing I'm going to say in this video is that this not only lets us divide, so here's my last note. Go away. Us divide something like 200 divided by 5 or equals 4, or we could say like 201 over 5. That's not 4. Who am I? 200 divided by 5 is 40, or 201 divided by 5 equals 40 with a remainder 1. And depending on your language, 201 over 5 might just kind of get rid of that remainder and ignore it. It might just be integer division, in which case we only care about this 40 number. But we also get do something like 200 mod 5 or 201 mod 5, which just cares about that remainder number. And modular arithmetic is really important. We may or may not see a lot of modular arithmetic in this class, but if you ever look into things like cryptography, some of the RSA algorithm for cryptography does a lot of interesting stuff with modular exponentiation and stuff like that. So modular arithmetic, really important, and you can do it, you can get that mod, which again is just telling you what's the remainder, you can get that using this division algorithm. So it's a really important algorithm. There we go. There's our proof of the correctness and the time complexity of the division algorithm.